When I mention the phrase special relativity, what comes to your mind? You'll probably think of Einstein, maybe even a few fancy equations. Maybe you're starting to panic and praying that I won't start talking about fancy math stuff that nobody can understand. It's okay though, because you do not need to have any prior knowledge in physics to understand special relativity. All you need is the willingness to give up everything you've ever known about time, because Einstein's theory of special relativity is going to make you do just that. But before we can understand special relativity, we must first understand the speed of light and how that relates to space-time. Special relativity is built almost entirely on the idea that light is traveling at a finite but constant speed, 299,792,458 meters per second to be exact. But how do we know that light is traveling at a finite speed? Perhaps 16th century astronomer Ole Roymer can tell us a little something about that. During his time, astronomers could predict when Jupiter's moons would appear in front of the planet from Earth's perspective fairly accurately. These events are known as eclipses. According to Gravity Probe B, a Stanford University website dedicated to the work of Einstein, Roymer found that there was a delay between these predictions and when he actually observed these eclipses. He figured out this delay was caused by the finite speed of light, because if the speed of light were instantaneous, then there would be no delay, and the light from the eclipse would arrive on Earth the moment that the eclipse happened on Jupiter. Now, we know that the speed of light is finite, but is it constant? To figure that out, we're going to have to look at the Michelson-Morley experiments. According to the University of Virginia's Galileo Einstein website, the two scientists arranged a half-silver mirror like this in the center and shined some light through it. The half-silver mirror would allow half the light to pass through, while the other half would be reflected like this. For reasons that would take way too long to explain involving wave-particle dualities and wave interference, if the speed of light were not constant, then these light rays, after being reflected back by these two mirrors here and here to the center, would not have rejoined. But the light waves did rejoin, meaning that the speed of light is constant. Now, space-time diagrams are useful tools in helping us understand and learn about special relativity. This is a space-time diagram. As you can see, as time moves on, the stick figure remains stationary while the car is moving at some speed. Because the stick figure is stationary, we are looking at this from the stick figure's frame of reference. However, we could also redraw the space-time diagram so that we are looking at this from the car's frame of reference, where the stick figure is moving away from it. Now, let's draw a different space-time diagram. Let's say that this figure is shining a light. The light, as you can see, is traveling at a constant speed, so therefore these lines representing the speed of light must always remain constant. However, if the figure were to start moving, then we'd have to shift everything to represent the figure's frame of reference. However, that means we'd also have to shift these lines representing the speed of light, which therefore changes the speed of light. We already know that this is impossible, so therefore it is impossible for things to be moving without changing the speed of light. But clearly movement is possible, and the speed of light always remains constant. So what gives? This is the part where Einstein comes in with his essay on the electrodynamics of moving bodies, where he proposes his special theory of relativity. In his essay, he proposes that we can rotate the time axis to look like this, so therefore the stick figure can still be moving, but the speed of light will still remain constant from any frame of reference. This rotating of time is known as a Lorentz transformation, where time is rotated to keep the speed of light constant. Now two events that seem to be happening simultaneously for a moving figure are now happening at different times for a stationary figure. This bending and stretching of time is known as time dilation. Okay, Einstein's description of special relativity is kind of abstract and hard to understand. I think Stephen Hawking does a much better job explaining things. In his book, A Briefer History of Time, he creates a thought experiment, which I'm going to modify a little bit to get my point across. Imagine that you have this box over here with mirrors here, and you have a photon, which you can think of as a particle of light, over here, bouncing between these two mirrors, right, like this. Now imagine that you have an exact identical copy of this box, and you put it on a moving train. From your frame of reference, the train's photon has a further distance to travel between each bounce than your photon, because not only does it have to move up or down, but also to the side along with the train. But since the speed of light is constant, that means the train's photon will take longer to bounce than yours, because the train's photon has a further distance to cover. Therefore, the train is experiencing time slower than you. However, if we were to look at this from the train's frame of reference, we could use the exact same reasoning to argue that you're the one that's actually experiencing time slower, because you're the one, from the train's frame of reference, you're the one that's moving away from the train, and therefore your photon has a further distance to travel. This is very, very counterintuitive to our everyday understanding of the world, but that's just how physics is, very counterintuitive. Now that you have a basic understanding of Einstein's theory of special relativity, you now know that time isn't what you always thought it was. And if that doesn't blow your mind, I don't know what will. Even if you did find this to be boring, you now at least understand that you don't need a PhD to understand special relativity.